Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
In Google, a popular search question is, who is Philip Emeagwali? I was born in the late afternoon of August 23, 1954, in Akure, in the heart of Yoruba Land, in the then British West African colony of Nigeria. I'm studied in the United States, where I reside, but I'm not studied in Nigeria, where I was born. In fact, it's easier to study Nigerian contribution to technology in US schools than it is to study Nigerian inventions in Nigerian schools. My Igbo-speaking parents, Nnaemeka James and Iyanma Agatha Emeagwali, were born and raised in Onitsha, colonial Nigeria, and lived briefly and independently in Kano, Nigeria of the late 1940s, and both speak the Hausa language. Who is Philip Emeagwali? I am the research massively parallel processing computational mathematician that discovered how to reduce the abstractions of mathematics to 65,536 computer codes that I synchronously emailed across what I visualized as a small copy of the internet. That's a global network of 65,536 processors. I am the research massively parallel processing computational mathematician that discovered how to make computers faster and make supercomputers fastest. I am the research massively parallel processing computational mathematician that discovered that what formerly took 65,536 days or 180 years to compute could now be computed in just one day across a new internet that's a global network of 65,536 processors, or across as many computers. It's often said that mathematics is the queen of sciences. I say that the partial differential equations of modern calculus is the crown jewel of modern mathematics. The partial differential equation is the most advanced and the most important expression in calculus. The partial differential equation was my first tour de force into modern calculus. On July 8, 1991, in Washington, D.C., United States, I delivered a pivotal lecture at the International Mathematics Congress called ICM 91. At that Mathematics Congress, I lectured on the system of 9 coupled nonlinear and time-dependent partial differential equations of modern calculus called Emeagwali's equations that I invented. The partial differential equations of calculus and their companion system of partial difference equations of algebra that approximated them are used from the construction of the tallest buildings in Lagos, Nigeria, to the construction of the second bridge across the River Niger at my ancestral hometown of Onitsha, Nigeria. In the 21st century, Africa must cross new frontiers of technological knowledge to conquer today's challenges. One of those new frontiers is the mathematical knowledge behind the parallel processing technology that makes the computer faster and makes the supercomputer fastest. The partial differential equations of modern calculus and its companion partial difference equations of large-scale algebra play an invincible but pivotal role in Africa's economic development. In the Niger Delta region of my country of birth, Nigeria, a detailed geological survey that included high-performance mathematical computations that were executed across an ensemble of processors was necessary to discover oil and gas that was buried 1 mile deep and buried in hard-to-discover places. The 81 partial derivatives that defined my 9 partial differential equations of modern calculus are symbolic representations of the inertial, pressure, viscous, and gravitational forces that govern the unseen subterranean motions of oil, water, and natural gas within the oil field. On my blackboard, these 4 forces are only visible to a few dozen people that were initiated into the mathematical priesthood of the system of partial differential equations that was at the calculus core of Petroleum Reservoir simulation. As a physicist and as a mathematician, I had to concretize my abstract calculus to physical forces. As a lone wolf massively parallel processing supercomputer programmer, my grand challenge was to experimentally discover how to make the previously impossible to compute possible to compute. In the 1980s, I had 64 binary thousand processors and had them in the decade it was considered impossible to use them to achieve a speed up of 64 binary thousand. That speed up that I achieved in high performance supercomputing is the equivalent of reducing 180 years of time to solution on only one processor that was not a member of an ensemble of processors to only 1 day of time to solution across an ensemble of 64 binary thousand processors. To perform my mathematical magic, that was the cover story of the May 1990 issue of the Siam News. That was the top publication of record in mathematics. Required that I get the correct mental picture of how to perform the magic and perform it across a new internet that I visualized as my global network of 65,536 processors that were married together as one seamless, cohesive supercomputer that was married together by 16 times as many, or 1,048,576 commodity email wires. I was the magician that made the invincible visible. I had to make the invincible 65,536 initial boundary value problems of calculus visible as 65,536 536 global circulation models, or visible as 65,536 petroleum reservoir models. I was the magician that made the invincible 2 to the power 16 email messages that I sent to as many 16-bit long addresses and made them visible at the as many vertices of the cube in a 16-dimensional universe. My lectures to research mathematicians were for experts who liked their mathematics uncensored and preferred matrices, tensors, and summation indices over words. My lectures to research physicists were for computational physicists who like their fluid dynamics raw. Here is a 3-minute version of my lecture of July 8, 1991 in Washington, D.C. that I delivered at the International Mathematics Congress that was the largest gathering of mathematicians ever. As an aside, the mathematical sophistication and the computational complexity of the extreme scale high resolution petroleum reservoir simulator has grown exponentially since the early 1950s. The oil and gas industry massively parallel processing supercomputer codes are proprietary. Those supercomputer codes are classified as trade secrets. For that reason, I do not have the liberty to share the petroleum reservoir simulation codes that I analyzed in the 1970s, in the 1980s. From analyzing actual production codes, I mathematically discovered that petroleum reservoir simulation codes are used with critical mathematical defects. I mathematically discovered that the system of coupled nonlinear and time-dependent partial differential equations of modern calculus that governs the initial boundary value problems that defines the mathematical core of petroleum reservoir simulators are defective. I mathematically discovered that they are defective by 36 partial derivative terms. Those mathematical defects, comprising of 36 partial derivatives, were replicated across the finite difference algebraic approximations of the continuous initial boundary value problems, and the mathematical errors that occurs in the extreme scale algebraic approximations were in turn replicated across the computer algorithms that was used to code the solution of the system of finite difference algebraic equations. In a mathematical nutshell, I contributed to the modern calculus that is used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I, Philip Emeagwali, pushed the frontiers of the partial differential equations by reducing it to its algebraic and arithmetical equivalences and coding it to its floating point arithmetical operations equivalence and executing those arithmetical operations across a small copy of the internet. I pushed the frontiers of calculus and algebra on the blackboard by inventing new calculus and new algebra. I pushed the frontier of arithmetic on the motherboard, experimentally executing the fastest arithmetical computations ever, and by emailing them across an ensemble of motherboards. I pushed the frontier of calculus on the blackboard and pushed it by a distance of 36 partial derivative terms that I invented to be used to recover otherwise unrecoverable oil and gas. But I mostly pushed the frontier of calculus across my small copy of the internet that I discovered is a global network of 64 binary thousand processors, or a global network of as many computers. At the International Mathematics Congress, I was cognizant of the fact that, unlike the pure mathematician, I am a physicist and a supercomputer scientist. And as a scientist and a technologist, I had to distinguish between a scientific discovery and a technological invention, and the burden of doing so for a mathematical community that we are unsure if my 9 previously unseen system of coupled nonlinear and time-dependent partial differential equations called Emeagwali's equations for all that flows underneath the surface of the earth should be classified as a discovery or as an invention. A method for solving partial differential equations may be a discovery in mathematical physics, but is not by itself a discovery in physics per se.
Insightful and brilliant lecture.